Okay, our next speaker is Amin Saberi. He is a professor of management science and engineering at Stanford. He received his bachelor's from Sharif University of Technology and his Ph.D. from Georgia Tech in computer science. His research follows algorithms, design, analysis of social networks, and various applications. He's a recipient of the Terman Fellowship, Alfred Sloan Fellowship, and multiple Best Paper Awards. Welcome, Amin.
Oh, thank you. Thanks for having me, and thanks for putting together a fantastic workshop. I'm going to talk about matching in dynamic environments, and you should feel free to stop me and ask questions anytime during the talk. Matching is the most central problem in algorithm design. It has roots in the work of mathematical giants like Euler and Kirchhoff, and it's been crucial in the development of theory of computing. If you look at Edmond's paper on finding perfect matchings or maximum matchings in general graphs, he also talks about this notion of good algorithms or efficient algorithms, what we call now polynomial time algorithms. Karp's paper that reduces combinatorial problems to each other, the problems that now we call NP-hard, has three-dimensional matching as one of the examples. And now with the advent of modern applications in online advertising, ride-sharing, online retail, algorithms are deployed to match the demand and supply for all these applications at a scale. And these new applications have been a source of several intriguing questions and very challenging open problems. So one of the main characteristics of these applications is that the matching between the demand and supply is not done in one shot. The algorithm has to make matching decisions between the two sides in real time and with limited information or unreliable information about the future. So in this broad area, I have been I've worked on a bunch of different applications to online advertising that Vijay talked about yesterday, and also matching and inventory management that Rod mentioned in his talk. Today, my focus is going to be on ride-sharing and ride-hailing applications. I'll tell you a little bit about what I've done here. It also has the advantage that over the past 2-3 years, I have had the pleasure of advising the marketplace data science group at Uber. And I've been directly involved in the launch of a few of the core products related to matching and pricing. So I'll tell you a little bit also about applications on the ground and the lessons learned over there. One feature of matching problems in the context of ride-hailing and ride-sharing is that typically the matching decisions don't have to be done immediately, unlike online advertising. So typically from the time you make a request for a ride, from the time you open your app until you're matched to a driver, the platform has around 1 minute. In ride-sharing, it could be 3 to 5 minutes. So the platform gives itself a little bit time to find other rides that have a similar route so that the two routes can be matched to each other. Now, that's not limited, restricted just to ride-sharing and ride-hailing. In online retail, from the moment you order something until it's matched to a car, a truck that's going to deliver it to you, sometimes it's a couple of hours or maybe days. In the context of maybe a kidney exchange, it could be a few years even between the time somebody needs a kidney until a matching takes place. When there is a deadline like this, when the matching decisions have to be done within a window, a common strategy is batching. Batching is this sort of simple idea of frequently looking at the market, look at all the vertices that can be matched to each other, finding the best matching there, clearing the market, and then coming back after a little while. And now, so actually, if you look at Uber's public web page, it talks about this. It talks about this innovation that they had, that initially they had a greedy matching. So when you requested a ride, they would match it to the best driver right away. And sort of the web page sort of explains that if you do the matching greedily, as you can see on the left, then maybe for the next request, there may not be any cars available that are sort of in the area. So for the second matching, you have to pay a significant cost. But if you wait a little bit and you do the matching, the two matching decisions at the same time, you can find a good solution for both of them. So the question that we asked was, is batching an effective strategy? What can we say about the performance of batching? And we looked at a simple random arrival model. Imagine you have a graph, n vertices, and for every pair of vertices, I have this W weight function that tells me what's the value of that can be gained from pairing these two vertices to each other. So think about these are ride requests. What's the value you gain if you put these two riders in the same car? So the graph sort of is arbitrary. The weights are arbitrary. Let's say it's determined by an adversary. And then once you have that, the vertices arrive in a random order. So at every time a step, a new vertex arrives, and it stays in the system for d steps. Now, two vertices can be matched if they're present at the same time. So think of every vertex as an interval. The two vertices can be matched if the corresponding intervals intersect. So the vertices arrive, and you can make matching decisions, and your goal is to maximize the expected weight of the matching, or the total weight of the matching, at the end of your algorithm. Now, batching algorithm, what does it do? Every d plus 1 steps looks at all the vertices that are available, that are in the market, finds the maximum weight matching there, clears the market, then waits another d plus 1 steps. Those vertices are gone, new vertices arrive. Again, you find the maximum weight matching, and so on. You want to compare the performance of batching algorithm with the optimum offline. This is the best matching that you can find in hindsight. You look at all the pairs, all the eligible pairs, you find the maximum weight matching, and you want to know how do these things compare. Yes?
So if a vertex remains unmatched in one batch, can it go to the second batch?
Well, the vertices stay only at, in the system for d steps. So when you go to the next batch, this vertex is gone.
No, but imagine at the end of one batch and the beginning of the next batch.
Yeah, but you do the matching decision at the end of every batch. So. Yes, so right now I'm assuming that my batch sizes are the same as the time the vertex is. They could, but if I was doing the batching more frequently, then the question and sort of your comment would be.
So if somebody comes at the end of your interval.
Yes.
Oh, I see. They're getting immediately matched. That's even better.
Yeah.
Okay, they don't need to see.
Right.
Also want to compare it with
Greedy is trivially bad. Yeah, because here the WIGs can be arbitrary. So the two. So as soon as the vertex arrives, you're matching it to the previous vertex, essentially. So that's equivalent of having batch sizes, obviously. Yeah, so that's bad. So here's our conjecture that for large enough n and d, the batching algorithm with batch size d plus 1 produces a matching with weight at least half of the optimal. And no algorithm can achieve a competitive ratio better than half. So essentially, as far as competitive ratio is sort of concerned, this is the best you can do. That's nice conjecture. But what we can do is the following. We can show that. This should be here, sorry. So not half of the optimum, but we can get something that's like prove that it's at least 0.279, 27% of the optimum. The proof, and I'll tell you just a little bit of it, uses techniques from polyhedral theory and combinatorics. Sure, it will actually be super clear in one slide or two. No problem. Thanks for proving half is an intriguing open problem. Imagine you have only one edge, so the Wij is non-zero for only one edge. The probability that it becomes eligible is twice the probability that it falls within one batch. Wait, one more slide. Two more slides and I'll get to it. So how does the proof work? First, we do, sort of convert the problem into a graph covering problem. And then we develop these amplification gadgets that if you have a proof for a small n, they would generalize it to large n. And if you have it for a small d, they would generalize it to large d. So once you have those, you only need to prove the competitive ratio for a small n and d. And we do that using a large linear program, using it's a computer-aided proof. All right, so how do I turn this problem into a graph covering problem? Think about a permutation. The vertices are arriving in a certain order. This is the support of the optimum solution. What is this graph? For every vertex, you connect it to all the vertices up to d steps before and d steps after. Essentially, optimum finds the maximum weight matching here. Now, how does batching work? Batching every d plus 1 steps finds the maximum weight matching. So the support of batching is this clicks of size d plus 1. Now, if I go back to the to the example, imagine if you have only one edge, the probability that this length is at most d, is going to be the value of optimum here. The probability that it falls within one of the batches is half of that. Now, how do we get a good competitive ratio? Essentially, what we do is that we look at this optimum of for this permutation pi, and we say we're going to try to cover it using these graphs. And we don't need to just use this particular permutation. We can look at a bunch of other permutations. If the collection of those permutations, you get a bunch of graphs. If you can put them on top of each other and get the graph of the optimum, then you can, using the standard techniques in linear programming on polyhedral combinatorics, you can say that the performance of the batching is, you can relate the performance of batching to performance of optimal offline. So if I want to be more formal, I say a collection of graphs is a cover for, collection of graphs h1 to hk is a cover for h. If you superimpose these graphs on top of each other, you get a super graph of h. Think of these as adjacency matrices. You just add up the adjacency matrices. If this entry y is bigger than adjacency matrix of h, then you're good. Now, if you have a collection of permutations, sigma 1 to sigma k, and you take a linear combination of the graphs corresponding to batch for sigma 1 to ck, and if that covers the optimum solution for some permutation, let's say identity, and some of the lambda i's are at most alpha, then you can say that batching is 1 over alpha competitive. Yes? Yeah, sure.
Where did the permutations come from?
So the permutations correspond to different runs of the algorithm, because all the permutations are equally likely. So I want to think about the performance of the algorithm for optimum for this particular permutation. I don't relate it to the performance of batch only for this particular permutation. I find 5 other permutations and say, oh, if the optimum is getting value of 20 here, the batch for this permutation and that permutation and that permutation also gets 20. How do I do that? By finding this cover. So what is the nice thing about this graph cover lemma is that I only now need to find a graph covering between this collection of graphs and that particular graph for the optimal. I don't need to worry about competitive ratios, weights. It makes the problem a simple graph problem. Okay, apologies to everyone else. Remember there was this paper by Vempala, and that were sort of trying to get a 4/3 approximation for the ATSP. They were using they would take the integer polytope and then they blow it up, and then they say if it includes all the corner points of the sort of the fractional polytope, then you can get a bound the integrality gap. This is very similar. It's just a stochastic version of that because you're looking at the random permutations. Oh, yeah, so you need a random order, a random permutation, and a uniform distribution over the permutations. We'll look at the worst case performance too. I won't have time to get into it, but I'm happy to tell you afterwards. All right, so let me do this part quickly. How do we go from a small n to large n? Essentially, we look at these periodic permutations, and if you can find a cover using this periodic permutations, and the graph that I showed you was a long line. It's actually easier to think of them as large cycles. And if it's periodic, it means that if there's a particular pattern that's being repeated, what you can do is that you can open it up and repeat it a little bit more. So you go from a small graph to a larger graph that way. So essentially, it says if you have an alpha cover of this CDN with a p-periodic permutation, as long as p divides n and n divides n prime, you can go from CDN to CDN prime. There is another gadget that we come up with, and that's vertex duplication. Imagine you have a small cover for some small d. If you duplicate the vertices, you will get a cover for 2d. You can also put 3 vertices and so on. So that will also give you another gadget to go from small constructions to large constructions. So then, for a small n and d, you can write these linear programs that compute the size of the cover. Even for d equal to 50, this will be a very large linear program, maybe with like 50 factorial constraints, but there are these standard techniques for bounding the size of a very large linear program. We use those to compute the alpha that I mentioned. For d smaller than 50, we show using the solution, by giving a solution to this LP, that alpha is less than 3.58. For d bigger than 50, using the amplification gadgets that I showed you, we showed that the loss is small. So this proves the competitive ratio of 1 over 3.58, which is the 0.279. Yes?
You check all the d's are smaller than 50, then let's say a prime number larger than 50, which is not really.
Yeah, so I didn't say it, but it was written that if you have a small, let's say if n doesn't divide n prime exactly, but there's a small remainder, you have a small loss. And that small loss becomes smaller and smaller for larger n, so we can control it. Yes, exactly. So and that's why we did an exhaustive search. Yes.
I have a naive question. So you have your batching approach and you have the hindsight optimum, right? So if I start the batch at a random location, right, there are d choices. So every edge in the hindsight optimum should be part of one of the batches with probability half.
That's correct. Still, it doesn't give you the factor half. I wish it did.
So what breaks?
It's because you find, okay, so for every single edge, this is true. But there is this complex correlation between all the edges. And you're looking for the maximum weight matching. I've tripped over this multiple times, and maybe I don't see it. Maybe there is actually a quick proof that would give half, and that would be amazing. That's what I was going to say, that maybe you can come up with better gadgets, amplification gadgets, and larger linear programs, and improve this a little bit more. But I don't claim that the proof that I presented to you is the proof from the book. There must be a simple, yes?
I have an even more nice question.
Oh, go ahead.
Why would an edge be with remain with probability half? Because when edge spans d time,
Yes.
you're taking a random
Well,
sliding window, then the edge will almost certainly go away, right?
no, so the edge, sort of the larger edges with, high probability they will go away. The shorter edges, they end up in the batch with a higher probability. So on average, an edge ends up. But then there are all these crazy dependencies that are introduced that at least keeps me from proving factor half. So here I'm assuming Wij's are non-negative. So the batch pretty much matches all of them to each other. Certainly. I don't, so if you add those assumptions, I don't think batching is the optimum way to go. Right, so this is, like I'm assuming some structure, but not a lot of a structure. When you have a lot of information, probably you can do like dynamic program or do sort of some. All right, good. So let me tell you about a related problem. Yes. Sure. So let's say in that case, you put them in separate cars, so it's 0. So it's not negative. You always have that choice. This is, sort of this is, paper on two-stage matching is with Roth and with Yiding Feng. And let me mention that Yiding Feng is incredible, and he's in the job market. So let's look at the baby version of the problem first. The problem is sort of in 2 stages. You have the set of cars. In the first stage, you have a set of riders. They come, they request a ride. You find the platform can pick a matching between the riders and the drivers. Then in the second stage, you get a second set of the riders, and you have committed to the first matching. So you find a matching between the second set of riders and unmatched drivers. And let's say your goal is to maximize the cardinality of the union, or you look at the vertex-weighted version. You want to maximize the total weight of the matched drivers. So this formulation tries to capture the dependencies between the 2 batches. So when you're sort of solving the maximum, when you're solving a sort of computing the maximum matching in the first batch, you can think about what are you leaving for the next batch. And the question is maybe among the different matchings, you can find one that's better for the future. So if you look at this problem, and it's actually very easy to observe, that you can't do better than 3/4 of the optimum. Imagine you have 1 rider and 2 cars. If you commit to one of the cars, the adversary is going to send another rider who's only sort of adjacent to that. So your best bet is actually to toss a fair coin and pick one of these 2 cars. So in that case, with probability 50%, you match both of them. With probability 50%, you match only one of them. So your competitive ratio becomes 3/4. And this simple example suggests that you want to do some sort of a balance approach. You don't want to, you want to make the probability of drivers being available in the second stage as large as possible, as even as possible. And for that, we solve this convex program, which is, these constraints are just matching constraints. We are just, we take a strictly convex function and we try to, minimize the G of the probability that a car is available. It doesn't matter what function you use, as long as it's strictly convex, it will give you the same solution, and it will try to balance the, make this So this essentially gives you a fractional matching, and it will try to make the fractions that it uses from each car as equal as possible. So in this example, you have a lot of choices for matching between the riders and drivers, but this convex program consumes only half of each car. So essentially it does some sort of a hedging, some sort of a balancing. So here's our algorithm: solve the convex program, get x star ij's, you get a fractional solution, interpret that as a distribution over integral matchings, sample a matching from that. That's your matching M1. In the next round, the next set of riders arrive, match those, and we can show that that would give you a 3/4 competitive algorithm. And there are different ways of proving it. You can use a primal dual analysis or take advantage of Edmonds-Gallai's decomposition for bipartite graphs. So far, simple. But you can build on this, so it becomes more fun when you realize, yes? This is a bipartite version. It's my problem. Yeah. Yes, yeah, right. So here the simple vanilla Berkhoff von Neumann works. So I was going to say that it becomes more fun when you realize that the second set of riders that are arriving, these are the people who have just opened their apps, right? They're about to enter the sort of destination into the app, and each one of them have some probability of requesting a ride. So you can actually say in the second, I have the graph for the second stage, and I have the probability of arrival. So with this sort of additional information, it becomes a two-stage stochastic matching problem. And we showed that you can get better than 3/4. It will be an approximation of the optimum online. And it uses the primal dual techniques. And you have to add some ideas from submodular optimization to do a little bit sort of better than 3/4. And then it becomes even more interesting when you realize that these probabilities, the probabilities of acceptance, is a function of the prices you quote to the riders. So your two-stage optimization problem is actually a matching and pricing problem. In the first stage, you can decide how to match these riders to the cars, and then at the same time, you offer price theta I to rider I. So imagine each rider has a private value that comes from some distribution that's known to you. So while you're matching this set of riders to drivers, you quote a price to the set of riders who are sort of about to make a request, and by setting the right prices, you can get just the right set or right number of riders to make a request. And now your goal could be maximizing the welfare of the riders plus drivers. So for this, we give a factor half approximation algorithm of the two-stage problem. And the technique is, it uses a more involved convex program than what I showed you, and the techniques in online contention resolution. Yes? Sorry, go ahead. Good. So depends on what you mean by price discrimination. So obviously, you can do discrimination based on the location of the riders, right? So some people are in these sort of zones that are the demand is much significantly higher than supply. But if you don't want to discriminate based on the name of the rider, right? So then you have to plug in the same distribution for all the riders in the same region. But in theory, if you want to do price discriminate, you can plug in different distributions. Yes?
So in the second stage, the final goal is social welfare maximization or revenue?
You can convert the two, right? Our focus here was the maximizing the social welfare. But in theory, you can also look at the maximizing revenue.
So in then
Because then you will have all of them accept the price. You don't know who values it more. And you have a limited number of cars. All right, good. One of the lucky coincidences while I was at Uber, Uber decided to rewrite, overhaul their real-time pricing. We came up with a matching-based algorithm for the real-time pricing. There were a number of amazing data scientists and engineers involved in this sort of large project, but the algorithm was by Leo Seaman and I, which sort of in early experiments did actually amazingly well, and sort of now it's implemented worldwide. So the real-time pricing is essentially what they call surge pricing. So next time you get a surge on Uber, you can thank Leo. There is also a related problem. This is for driver pricing that we looked at for matching, sort of matching and pricing delivery jobs. Yes.
So I guess going back to the previous slide, so when you do something like this for Uber, are you using data, or are you just doing sort of like?
You're using data. You cannot really assume that these are, sort of distributions and the arrivals are independent from each other. And like here, I assumed, for example, that sort of these are the private value sample from the same distribution. Essentially, I assume they are independent from each other. But all your users are responding to the same environmental situations. Like, for example, if it's raining, everybody wants a car. So you really can't. And if there's time, I'll talk about it. Like, what's the difference between when you're modeling a problem, when you want to prove something about it, versus when you're sort of coming up with an algorithm that needs to be implemented and used. So this is for matching delivery jobs. So think about food delivery. You have a set of jobs. These are the sort of the food orders that are about to get ready. You have the set of drivers, and the platform has some value for the delivery of a sort of the food item to the user. When the food is about to get ready, what it does is that it will go to different drivers and start shopping for the right driver. So it goes to a particular driver and says, I'll pay you a certain amount of money to go pick up that sort of food and deliver it. So we assume that that we know this probability, so that we know that the driver sort of accepts with probability Pijw. If you say, if the driver is J, you say go pick up the job I at the price W. So the orders become ready in certain order. The food becomes ready the food orders become ready in a particular order. You go, you do the shopping, and your goal is eventually to find a matching that maximizes your revenue. And your revenue is some of the values minus the cost you have to pay for the delivery. This was also inspired by, so this is a theorem with Tristan, Mohammed, and David Weitz that we showed there exists an efficient 0.456 approximation algorithm for the optimum outline for this sequential pricing problem. And the main technical idea is to improve the existing online contention resolution for matching in the weighted edge arrival model, the vertex-weighted, edge-weighted edge arrival model. And that was inspired by another project that I was involved in for driver pricing. This is at Uber Eats. That's why now the project is called Laminator instead of Laminor. So this is not fully deployed. It's now at the level of being tested on, in different markets. Okay, so takes me to this, to answer to your questions that all models are wrong. Some are useful. My main So my main takeaway lessons from this detour was first, these simple combinatorial models that you come up with, and they result in often result in elegant algorithms. Their insights are also extremely useful in practice. That's like a good news for somebody who has dedicated his career to developing algorithms. Some of the algorithmic ideas that I presented here have been sort of crucial in the development of things that got implemented, and they had sort of led to significant improvement in performance and market efficiency. Having said that, as a community, I think we need to continue examining and critiquing some of the dominant paradigms for evaluating and benchmarking and comparing different algorithms, especially online algorithms and using competitive analysis. For a couple of reasons. One is that often optimum offline that you want to compare yourself against is such an ambitious benchmark that most algorithms are just bad. Like for most problems that you start with, most likely the best competitive ratio that you can come up with is unbounded. Then you have to think about the special case. And even then, for the special case, you get stuck too early. You come up with a simple algorithm and it gives you maybe the best competitive ratio, and there is this wide range of algorithms that you cannot compare against each other because you're comparing against something that's so far away, so ambitious. But maybe more important, the algorithms that are designed in the designed against adversarial input, and also input by an adversary that's very powerful, are going to end up being very conservative. Are going to make very conservative choices. And in a lot of real situations, maybe they are too conservative, in the sense that the nature is not always working against you. Most of the time, the nature is just oblivious to you. And also, a lot of these algorithms don't take advantage, by their nature, don't take advantage of the increasing availability of past data or computational resources. So if you say, oh, we have 10 times as much data and 10 times as much computational resources, you don't know what to do with them. Compare that against machine learning algorithms that are hungry for more data, hungry for more, computational power, and they get better. So that's one of the reasons my focus over the last few years has shifted from doing competitive analysis to approximating optimum online. So when your input, the input to your algorithm is stochastic, is not adversarial, a better benchmark is optimum online. This is you can write the optimum online as a exponential size dynamic program, often referred to as Bellman's equation. So that's huge. And then you can ask, well, that takes exponential space, takes exponential time. How best can I approximate this? So it moves the problem from the realm of competitive analysis to the realm of approximation algorithms. And in approximation algorithms, we have a wide range of techniques that we can apply to this problem. So I have worked with on a bunch of examples from online matching to online Bayesian selection. It's actually nice that you can write new linear programming relaxations that have additional constraints that correspond to the performance of optimum online. In some cases, we can write these linear programming hierarchies that capture the performance of optimum online, to get closer and closer to it. And as a result, we can get polynomial time approximation schemes as opposed to constant factor or worse competitive algorithms. One example that's probably most relevant for this talk is the online stochastic matching. It's very similar to the problem Vijay talked about, except that the arrivals of the, let's say, the riders is from a distribution. So at time t, you have a rider I that arrives with probability pi. In this case, the algorithm should match it immediately. The goal is to maximize, let's say this is the weighted version, and the goal is to maximize the expected weight of the final matching. If you look at this problem from the point of view of competitive analysis, 50% of the optimum is the best you can do, but you can actually do better. So one thing that we did was that first we just asked, what is the computational complexity of optimum online? With Christos Papadimitriou, Tristan Polner, and David White, we showed that online stochastic matching is PS-space complete. So it's a little bit harder than NP-hard problems. But it's possible to approximate it. So we gave an algorithm with approximation ratio strictly better than the best achievable competitive ratio of 0.5. So we showed that if you want to get competitive, it was actually known that if you want to sort of come up with the best optimum, best online algorithm against the best optimum offline, you can do better than 50%. As a proof of concept, we showed you can do better here. You can write a better linear program. You can round it. This was in 21, EC21, and EC22. Mark Braverman, Mahsad Rakhshan, and Lovett showed that not only it's better, you can do better than half, you can get a 1 minus 1 over E. So you can get significantly better against this benchmark. We are now working together for some special cases. We can get even better than 1 minus 1 over E. And for some problems in online Bayesian selection or profit inequality with Rod and others, we actually managed to better characterize the structure of optimum online and managed to give polynomial time approximation algorithms using hierarchies of linear programs. All right, so to sum up, ride-sharing applications have given rise to many algorithmic problems. Rider pricing, driver pricing, matching rides to each other, matching rides to drivers, driver positioning, scheduling routes, matching and pricing for mid and large capacity vehicles. They actually, many of these are related to classic problems in optimization, from matching to facility location to traveling salesman problem. They also have a new twist to each one of these problems. So there's something new to be done for each of these. And there is potential for impact, for significant impact. Some that I talked about was more about optimization questions. And it's actually fun to come up with better matching algorithms, even if you reduce the waiting time of the drivers by a little bit, or reduce their driving time, you can save a tremendous amount of gas. Like you can really see that you're helping the environment. But maybe also in academia, we can do focus more also on policy questions, like how can you come up with policies that induce platform competition? How do you protect consumers? How do you protect the labor? And as I mentioned, in order to continue to be relevant and continue to make an impact, we need to revisit some of our modeling practices and standard paradigms for design and analysis of algorithms. I have a lot more to say about this, but maybe for another talk. I'll stop here. Yes.
So if you go back a few slides to your takeaway message.
Sure.
I want to say something related. So I really like the work you've done, and in particular, the impact you've had it's incredible. So your first takeaway lesson is look for elegant algorithms and
yes.
insights. So in that spirit, I gave my student a question, Thorben Tropst, and he has a paper with Rajan Udvani from Berkeley, which they submitted to Wine. And the question is the following. You have hyper edges coming. Each hyper edge is a car and 2 riders. So the riders are sitting here. But online, a car and 2 riders come. And you want to irrevocably match if you can. What's the best approximation ratio? So I want to take the whole thing back to 1990 when online matching was done to doing online hypergraph matching.
Right.
And what on computative ratio. So they have a paper where they study this through many angles, including fractional and integral. And I'm not even familiar with all the results, but they have a very nice paper that they submitted to Wine. So I just want to say that some basic insight like that, I mean, before we throw in deadlines and weights, which are, of course, needed for your application, let's just study the simple problem first.
Right, the hypergraph matching. Sure. Yeah, the interesting thing about sort of online matching is that depending on the capacity of the matching, the assumptions you have about the arrival,
Everything
whether it explodes combinatorially. So there is sort of no shortage of amazing problems in this domain.
Yeah.
Okay, I'll just ask mine. So, I mean, like in the same spirit of this takeaway lesson stuff, right? I mean, a lot of these problems arose in switch scheduling in the late 90s. And even there, like comparative analysis is too weak. And if you look at it more from simulation and do these heavy traffic approximations, it tends to tease out the differences between different algorithms. Do you have any thoughts on whether like those kind of queuing heavy traffic things are the right way to look at some of these issues, or?
Yeah, so for sure. But that still captures one aspect of this. I think there is a lot of, in those models and also in algorithms, we first of all, we force a particular structure on the problem, and then there are these parameters that we expect someone else to go measure and come and tell us. Now, think about machine learning. They say, oh, give me all the data, give me the raw data, and I'll try to extract the right features. Now, a lot of the things that they do is like, dark, art. But still, if you think about, sort of our paradigm, we are losing a lot in the modeling assumptions and in those, sort of measures. What's the right interface between the two? I think that's a very, sort of important question, and that's a very interesting question. So when I say, that was sort of my point that we need to rethink those. Nicole?
So in relation to the second bullet on this slide, I think the algorithmic ideas I saw in this talk were batching and maybe thinking ahead a step or so in your two-stage stochastic stuff. And at least for the batching, you kind of implied in answering an earlier question that in reality, the weights are drawn from some distribution and you should be using that. And so I guess there's a little bit, I know you can't tell us exactly what you did at Uber, but there's a little bit of a disconnect because it feels like you're not really committing to saying they should do batching. And so I still have a little bit of trouble seeing where the elegant theory moved into the practice. Like, what was the idea you gave to the intelligent data scientists that they then went and implemented?
Yeah, it's hard to say, hard to be, sort of specific, but a lot of these ideas about, sort of identifying the right optimization problem and relating that to the performance. Those are actually very critical. Now, how do you solve, what's the right convex program that you solve, let's say, or what's the right nonlinear program that you solve? That depends on a lot of the, sort of parameters that I don't have, sort of, in a simple model I don't want to get into. So the program that you end up solving is far more complex, and you don't feed it these numbers that I assume I have. You feed it some data, or you feed it some, neural network. But the main, sort of thinking that came from the simple model is still, is the core of the algorithm that's implemented.
The main thinking being like write down a program, linear program, or convex program.
Sure. Yeah, so it's a risk that I was aware of when that you can get into it, but only to a point. And I apologize, I can't get more into the details.
Maybe I'll try to probe you more on that line. I mean, I have been interested in kind of beyond worst case type of thing. That just kind of you're hinting on the second part of it. Sure. And I have been wondering, like, what are the distributions that occur in practice, right? Like, and I'm just curious to kind of, if you have observed from this data that there are some distributions that we study are really relevant in let's say this context, or any insight along those lines. I'm just curious about it. Only if you can share, of course.
No, I mean, So there are some things that you observe. For example, one of the best predictives of the immediate future is the recent past. Yes, because it changes. So maybe instead of a uniform distribution over the permutations, one has to think about invariances that are like that. But what's the distribution of the distances? It varies so much from one locality to another that you're really looking for algorithms that work well on the variety of sort of. You really can't have an algorithm for a small city versus a small town versus a big city, for Manhattan versus Los Angeles. It will be impossible to maintain different algorithms for this. So you're really looking for a matching and pricing algorithm that works under all of these circumstances. Okay.
Thank you again.
Yeah. Thanks.